In this section 5.4, we're going to look at some properties of functions with powers and roots that we really didn't touch on before. It's going to be a very short section. So I know in example 1, we did evaluate expressions that had negative exponents or even rational exponents. But just as a review, if you have rational or fraction exponents that are also negative, one way that you can simplify is to make the exponent positive by dropping it or flipping it to the bottom. So it's 27 to the 2/3 in the denominator of this fraction. And then if you're evaluating without a calculator, it's always best to do the root first because that gives you a smaller number, and then do the exponent last. So here the root is the denominator 3, so it's going to be 27, and then we're going to have the cube root. And we'll do that first. So we'll do the exponent, which was 2, last. And now remember, this is all in the denominator of this fraction. So when we take the cube root of 27, we just get 3. And then when we square that, we get 1/9. Again, we're not going to spend much time there. And we'll look at another example that we really didn't spend much time with. So if I wanted to simplify this expression, then I could switch it to rational exponents. Notice that underneath this square root, we have x times the cube root of x is x to the 1/3. And then remember that square root is the 1/2 power. So this is x times x to the 1/3 to the 1/2 power. So at this point, you could get rid of the parentheses, or notice inside the parentheses, you have x to the 1 times x to the 1/3. So if you add those exponents, you would get x to the 4/3. And then multiplying by the 1/2 exponent on the outside, you get 4/6, which reduces to 2/3. So x to the 2/3. So again, just expanding on some properties that we didn't spend very much time with in previous sections. Something else that we really didn't talk about is determining the domain of a root function without a graph. So if you just had the equation, like in example A, this is a 4th root. So remember that whenever you have an even root, what's underneath cannot be negative. So to figure out the domain, all you're going to do is take what's underneath the root, which is the 2x minus 5, and set it greater than or equal to 0, and that will give you your domain. Now in example 3, I have 2 examples with even roots. I don't have any examples of finding the domain with odd roots, because remember, with an odd root, like a cube root, you can have negative numbers underneath, positive, 0. Doesn't matter, domain's going to be all real numbers. So now here, isolating the x by adding 5 to both sides and then dividing by 2. So typically we would write these solutions in interval notation when we're looking at the domain. So everything greater than 5/2 would be a bracket because we're including the 5/2 to positive infinity. We'll look at another example in part B where we have an even root. This time we have a square root. So again, the x squared minus 25, that can never be negative, which means the domain is going to be everything greater than or equal to 0. So I don't want to just add 25 to both sides and square root, because remember, if you square root, you're going to get a plus minus 25 on the other side, but this is not an equation, this is an inequality. Is the sign going to stay the same direction? Is it going to flip? So instead, when we have these quadratic inequalities, the strategy is to factor, and then choose that equation, remember those would give us our points and split up our number line. So we have x is equal to -5, x is equal to 5. Those would be the points that we would use to break up our number line. And then we can use the -5 and the 5 if we put that in. So remember, we're putting these values into the inequality. If you put in 5, you get 0 greater than or equal to 0, which is true, and -5 would give you 0 greater than or equal to 0, which is also true. The intervals that could possibly be our domain would be -infinity to -5 with a bracket. We could look at -5 to 5, and also 5 to infinity. And we pick our test points. Something smaller than -5, I would use a -6. Between -5 and 5, 0. Greater than 5, +6. Again, we're putting these test points into our inequality. If you put in -6 and you square it, you get 36, which would give you 11 greater than or equal to 0. And I could use, which is true, so I could use anything in this first interval. When you put in 0, you're going to have -25 greater than or equal to 0, which is false, so cannot use. And then if you put in 6, you will also get 11 greater than or equal to 0, which is true, so I can use anything in that second interval, which means my domain will be -infinity to -5 with a bracket, union 5 to +infinity. Okay. Another topic that we want to explore further is transformations with these root functions. Recall in an earlier section, I had emphasized writing our functions in the correct way so that we could identify our transformations. And the book really didn't do it at that time. Here in this section is where the book does address writing the function in the correct way. And when I say correct way, I mean that the coefficient on x needs to be 1. In example 4, the coefficient on my x is 3. The first thing I want to do here is I want to factor out the 3 to rewrite this as y equal to negative square root of 3 times x minus 7. So now that I have the coefficient on x is 1, I've factored out the 3, I can identify my transformations. And now the order that you typically would do a transformation is the order of operations. Imagine putting in a number for x. The first thing you're going to do is that -7. So that's going to be a shift right. The next thing you would do is multiply by 3. That's going to be a horizontal shrink. Outside of the square root, you have a negative. That would be a reflection about the x-axis. And then the +9 would be a shift up. So let's go ahead and review those transformations now that we do have our function written in the proper order. So this would be the x minus 7. That's going to be our shift right by 7 units. I'm just going to write by 7. And then the 3, we're affecting the x value. So that's going to be a horizontal shrink or stretch. And since it's affecting the x, it's going to do opposite of what we think it's going to do. So instead of being a stretch, instead of the 3 making things bigger, it's going to make things smaller. So it's going to be a horizontal shrink by actually 1/3. So horizontal shrink. And then going outside the square root, so function's already done its square root job. Everything else is just directly affecting our y values. So the negative outside the square root is going to change y values from negative to positive, positive to negative, which means we're going to reflect across or about the x-axis. And then that plus 9 is going to shift our y values up by 9. So shift up 9. Or 9 units if you want to do that. But again, remember, I am lazy. So another way that we can look at these square root functions is by using this property that whenever you have a product or multiplication under a square root, you can split it up into two pieces. And it might be more helpful to do this when you're graphing this type of function because horizontal shrink and stretch are typically more difficult to understand than a vertical stretch or shrink. Going back to when we factored out the 3, I'm going to rewrite this as y equal to negative. I'm going to break this up into the square root of 3 times the square root of x minus 7, which I'm allowed to do. But now that I've pulled that square root of 3 out from the square root of x minus 7, that's our function with the x. So once that's done, that square root of 3 on the outside is just affecting the y value. That changes from a horizontal stretch shrink to a vertical stretch shrink because we've moved that number out from underneath the square root function. So now what we have is still a shift right by 7. So that's still going to be our first transformation. But instead of a horizontal shrink, what we're doing with that square root of 3, which again, the square root of 3 is greater than 1. So it would be a stretch. Is we're changing this to a vertical. Oops, I don't want that there. Vertical stretch. And by square root of 3. That's exactly what you think it should be, which is nice. Okay, so remember, working inside the function, things are doing the opposite of what you think they should do. Once you're outside of the function, it's exactly as you're reading it. So we're still going to take that negative and reflect about the x-axis, and we're still going to take that plus 9 and shift up by 9. Okay, again, just as a reminder, you can always check all of these graphs by looking at your graphing calculator or graphing utilities such as Desmos. Another thing that we really didn't talk about are parabolas that opened left and right as opposed to up and down. And that's because parabolas that open left and right, they're not functions. However, if we were to graph a parabola opening left or right, the process is still the same. So notice in example 5, instead of saying y is equal to x squared plus 2x plus 1, we instead have x is equal to y squared plus 2y plus 1. So since the y is squared and the x is not, that tells me that this is going to be a parabola that opens left and right. Something to note that this is not a function. It's not a function because it will not pass the vertical line test. But let's go ahead and see how we would graph. Similar to parabolas opening up and down, first thing we want to identify is our A, B, and our C, and those would still be the same. So the A value is 1, that would be the number on your y squared. B is 2, and then C is that constant value 1. So is this going to open left or right? You look at your A value. If A is positive, which in our case, A is positive, it is greater than 0 because it's a positive 1. So if A is positive, it's going to open right. So since it opens right, I'm going to have that image in my mind of a parabola that kind of looks like this. The next thing that we always find when we're graphing is our vertex, because that tells us where to start. So that's going to give me my starting point, and then I'm going to draw a parabola opening to the right. But this time, instead of using x equal to negative b over 2a, you're using y equal to negative b over 2a. And in our case, that would be a negative 2 over 2, or negative 1. So we need the x value that goes with that. We would put the negative 1 back into our equation to get negative 1 squared plus 2 times negative 1 plus 1. And then that should give us 1 minus 2 plus 1, or 0. Just be careful you're not graphing the point negative 1, 0. Remember, when we're graphing, we're still using the same order x, y. So the point that we're graphing is 0, negative 1. Let me go ahead and put that point on the graph. At this point, if I was graphing up, down, I would find my axis of symmetry, which would be a vertical line. But now we have an axis of symmetry that is a horizontal line. And that horizontal line is going to pass through our vertex. Since it is a horizontal line, the equation is going to be y equal to negative 1. It's the y value of the vertex, and this is going to be our axis of symmetry, which is good. Because when we find more points so that we can finish our graph, if we have a point above our axis of symmetry, we'll find its mirror image below the axis of symmetry. Let's go ahead and find some points. So I already know that I have the point y equal to negative 1, x is equal to 0. So I want to pick y values close to negative 1. 0 seems appropriate. So the question comes up, why am I putting values in for y? Wouldn't it be easier to put in values for x? And no. If I put in a value for x, so let's just say I put in x is equal to 0. Notice that I'll get y squared plus 2y plus 1 equal to 0, and I have to solve a quadratic equation, which can be complicated in order to find those y values. It's much easier, since the y is squared and the x is not, to put in values for y. So notice if y is equal to 0, right away I get x is equal to 1. But as a reminder, remember you're graphing the point 1, 0, not 0, 1. So when x is 1 and y is 0, I also get, through the axis of symmetry, the point 1, negative 2. And now I could basically sketch my graph, but maybe I want to find a few more points. It might be helpful, instead of finding points the way I've been doing by just putting in the y value and then finding the x value, is to make a table of values if you find yourself graphing in the wrong order. So remember, with our vertex, we put in y is negative 1 and we got back an x value of 0. So if I were to graph it, it would be in the correct order, 0, negative 1. Then I put in a y value of 0 and I got an x value of 1. So maybe I'll put a y value of 1. If I put in 1 for y, I get 1 plus 2 plus 1, which would give me 4. This is going to pass through 4, 1, and then I have 2 away across the axis of symmetry. I get another point. And at this point, it's time for me to graph my parabola. And again, notice this is not a function. It does not pass the vertical line test. So this is not a function, and our goal is to be able to work with functions. So how would I get a function? Well, what I would do is I would break up that equation, that graph, along the axis of symmetry. What the axis of symmetry does is, if you look above at that upper piece of the graph, that is a function. It passes vertical line tests. And if you look below, you have another function that passes vertical line tests. So what we're going to do is find the equation for the upper part, and I'll call that y sub 1, and the lower part, which would be y sub 2. And all I have to do now is just take my original equation, which was x equal to y squared plus 2y plus 1, and solve this equation for y. So the first thing I want to do is I want to check the y squared plus 2y plus 1 and see if I can write that as a perfect square, y plus or minus something squared, because that will make the algebra a lot easier. And in fact, this is a perfect square trinomial. This is y plus 1 in parentheses quantity squared. I'm going to rearrange this. I want to have my y's on the left. You don't have to, but it just looks better for me. And now my goal is to get the y by itself. At this point, I could just square root both sides. So if you do have a perfect square trinomial, it makes the computations a lot easier. Because if I were to square root both sides, don't forget you need a plus minus in front of the square root of x. Then the square and the square root will cancel on the left. I will just have y plus 1 equal to plus or minus the square root of x. And now all I have to do to get the y by itself is minus 1 from both sides. Typically, we would put that in front of the plus minus, but it really doesn't matter. So the plus minus is giving me my two functions. The plus would give me the upper function, the minus gives me the lower function. So I have a y sub 1 that would be equal to the negative 1 plus square root of x, and the y sub 2 would be the lower half, the negative 1 minus square root of x. And if you're not sure if you've broken it up correctly, just go ahead and put in some values for x. Well, if x is 0, we get this same point on the graph, which is 0, negative 1. If x is 1, then we get the upper graph, where y value is 0. If x is equal to 1 and y sub 2, we get a y value of negative 2. So we did break it up correctly. So we're going to continue with this idea of breaking up graphs or equations that are not functions into pieces that are functions. And the goal is to work with functions. We always want to be working with functions that are really nice. Because in a function, if you put in one value, you just get one value back. You don't get a bunch of different choices, which is what we want. In example 6, we're going to describe the graph of the equations that we have as either a circle or a parabola. And then we're going to split the equations into two functions. In part A, I notice that I have a y squared, but the x is not squared. So if you don't have an x squared and a y squared, then it's not a circle. It must be a parabola. So part A is a parabola. And it's a parabola that's opening right. And B, I have the x minus 2 squared. So I have an x squared and a y squared. This must be a circle. So I've identified these as either a parabola or a circle, and now I want to define functions. In A, the first thing I want to do is check the y squared plus 4y plus 5 and see if I can write that as something squared. But unfortunately, it's not a perfect square. So we'll look at two ways that we can make it into a perfect square. The first way would be to, and I'm going to rearrange this and write the y squared plus 4y on the right-hand side, because my goal is to solve for y, so I like to have it on the, did I say right? Left-hand side. And then I'm going to put the x on the right. I'm going to minus 5 from both sides. So I have the y's together on one side and the x's and the numbers together on the other side. And then I'm going to go ahead and complete the square on the y's. So remember what we do, we take half of the number on the linear factor, which is y, and we square it, which gives us 2 squared, or 4. That's what I'm going to add on the left. I'm going to add a plus 4 so it turns into a perfect square. But I can't simply add a quantity to one side without adding it to the other side as well. I have y plus 2, oops, I said 2 and I wrote 1. Y plus 2 squared on the left-hand side and x minus 1 on the right. So now that I have something squared, I can square root both sides. Remember that when we do square root, we have to add in the plus minus to get y plus 2 equal to plus or minus the square root of x minus 1. And then I would minus the 2 from both sides, and I have my two functions. Maybe I'll call one function y sub 1, and that would be the negative 2 plus square root of x minus 1. And maybe the y sub 2, I'll call that the negative 2 minus the square root of x minus 1. Now, if you saw from the beginning, and let me go ahead and rewrite our x equal to y squared plus 4y plus 5. If you had looked at that and ignored the plus 5 and said, oh, if it was a 4 instead of a 5, it would be a perfect square, then you could have simply gone y squared plus 4y plus 4, and then the 5 turns into a plus 4 plus 1. That way, if you're looking at the y squared plus 4y plus 4, you can see that that will factor as y plus 2 squared plus 1. And at that point, you would minus 1 from both sides. And then square root both sides as we did before. You don't have to complete the square. If you can see that you can break that constant up, in our case, the constant was 5, so that we do have a perfect square, and in this case, we had the plus 1 left over, then you can isolate the y that way. Let's go to B, where we have our circle. Again, the goal is to solve for the y. In this case, it's real simple. I would just take the 36 and I would subtract parentheses x minus 2 squared from both sides. Again, goal is to get the y by itself so we can define our two functions. And at this point, we would simply square root both sides. Don't forget the plus minus. So we're going to square root all of this. 36 minus x minus 2 squared. And then we would have y equal to, I want to put this in back, y1 equal to the positive square root of 36 minus x minus 2 squared. And then the other function would be the negative. And that's it. That's how you get your two functions, is you do the plus minus, and then you'll have a plus and a minus function. Now, I'm not sure. My lab might have you multiply the x minus 2 squared out and maybe combine some like terms, but I'm okay with us stopping with this. So that's all we were going to do in this section, is just expand upon some of the ideas we had before. And that's it. Notice if I put in x value of 0, they share that point. So if you put in x equal to 1, the upper graph will pass through a y value of 0, and the lower graph will pass through a y value of negative 1. So I have them correctly labeled. So we're going to continue with this idea of breaking up